Alright guys, let's go ahead and get started with Newton's second law problems and talk about how we can approach these problems and how we're going to end up solving them. So the first problem that we have here is a dog pushing a 2-kilogram tennis ball at a constant velocity with a force of 10 newtons, and we want to find out what the force friction and all the other forces are acting on this tennis ball. So when we have problems like these, we want to make sure that we are approaching all of them in the same way. So let's take a look at our steps really quick. Step number 1 is to draw a picture and the free body diagram. So here's my picture. Yeah, I drew that. It took me a little while, but you know, I'm just great at drawing. So now I got to go ahead and make my free body diagram for that. So I'm going to do that right here. The important thing to note is that I'm making a free body diagram for the tennis ball. So looking at my problem here, I'm going to see if there's any important information up here that I need to bring down my free body diagram. I see the tennis ball has a mass of 2 kilograms. That's important, but not for my free body diagram. I see it's moving at a constant velocity. Constant velocity is telling me that it's going to have a balanced force. It also says that there's an applied force of 10 newtons, and it wants me to find out what the force friction and all that other stuff is. So it's telling me that there's force friction acting on it. So before I go ahead and label all my forces, I need to go and set up an origin. I'm going to have an origin that points up for the positive y direction and to the right for the positive x direction. Now I'm going to go ahead and label force gravity pointing down. I see my ball is on a flat surface here. So therefore, it's going to feel a force normal pointed perpendicular from that surface, in this case, straight up. See that my dog's on the left side of the ball, so it's pushing it to the right. So I'm going to have force applied to the right over here. And then lastly, I'm going to have force friction coming back on it. I know that force friction and force applied are going to be the same size because it says that it's moving at a constant velocity, so these two are balanced. Same with force normal and force gravity. I know that those are the same size because I know that it's balanced in the y direction as well. Now that we have our free body diagram, we can go ahead to our next step. Step number 2 tells us that we need to use our free body diagram to write our net force equations. Almost forgot about force friction over here. And we can denote force friction as Ff, or we can write F mu. Both of these mean force friction. Either way is fine. Now I'm going to go ahead and write my net force equation for the x direction. So I have net force in the x is equal to the forces that point to the right. That would be force applied minus the forces that point to the left, force friction. And we know that's equal to mass times acceleration in the x direction. Since this is balanced though, that's telling me that acceleration in the x direction is 0. Therefore, force applied minus force friction is equal to 0. That just means that force applied equals force friction. Now we can go ahead and do the same thing for the y direction. For the y direction, I have net force in the y is equal to the forces that point up, force normal, minus the forces that point down, force gravity. And that's also equal to mass times acceleration in the y direction. I know that this is balanced in the y direction because I'm not speeding up in the y or slowing down in the y. And my direction also isn't changing in the y direction. That ball is staying flat on the ground, so therefore my acceleration in the y direction is also 0. That just tells me that force normal minus force gravity is equal to 0, which means force normal equals force gravity. The next thing we're going to do is make a table of the x and y forces, just like we would have did with kinematics when we did 2D kinematics and we made a table and filled in our givens and our unknowns. So in the x direction, the two forces that we have are force applied and force friction. In the y direction, we have force normal and force gravity. It tells us in the problem that we're applying a force of 10 newtons, so we know that force applied in the x direction is just 10 newtons. Now if we look at the y side, we can remember that force gravity in the y is just equal to mass times gravity. Since the ball has a mass of 2 kilograms, and we know that we're on Earth and Earth's gravity is 9.8, we can easily solve for force gravity. We find out that the force of gravity of the ball is 19.6 newtons. Now we'll notice that in our table, we're missing force normal and missing force friction. What are we going to have to do now? Well, we're going to have to use our net force equation to solve for those unknown variables. So we kind of already did that before, and we can see that right here. We have force applied is equal to force friction. So therefore, force friction is also 10 newtons. And we also did that down here for the y direction. We have force normal is equal to force gravity. So force normal is 19.6 newtons. And there's our first problem. Piece of cake, right? The main thing that we have to do here is remember to split up our x and y directions, look for keywords like balanced, and then plug in our given variables. This question was pretty easy because everything was balanced, but let's take a look at another question where it might not be so easy. Let's take a look at our second example here, where we have a dog pulling a 30-kilogram box so that it accelerates at a rate of 2 meters per second squared, and the force of friction between the box and the ground is 30 newtons. So the first thing we want to do is go ahead and draw a picture and start labeling our free body diagram. We can see here in this problem that it says a dog pulls a 30-kilogram box, and I added this little part with a rope for clarity so that we know exactly what forces are in this problem. Before I draw that free body diagram though, I need to label my photo. So on my picture, I'm going to go ahead and draw my origin, show that up is the positive y direction like always, and to the right is the positive x direction. These things are implied, but it's always good to mention them again. I'm going to go ahead and draw my free body diagram for my box. I see that my box is on a planet, therefore I'm going to have force gravity pointed down. I also see that my box is on a flat surface, therefore it's going to have force normal pointed up from that surface. I know that force normal and force gravity are the same size because I know that this box is not accelerating in the y direction. It doesn't tell me that in my problem. It does say that the box experiences an acceleration at a rate of 2 meters per second squared, but it's because the dog is pulling it. We can see that the dog is pulling it to the right here, so we know that it's not experiencing an acceleration up or down. Next, I'm going to label my forces acting in the x direction. I see a rope, which means that I'm going to have force tension pointed to the right. And then back to the left, I'm going to have force friction. It's important to note that the box is accelerating. So what does this acceleration mean? Well, the accelerating is just referring to the fact that there are unbalanced forces here. That's going to tell me that force friction is smaller than force tension. Now that I've drawn my free body diagram and I've labeled all my forces, I can go ahead to my next step, which is using that free body diagram to write my net force equations. So let's start with the y direction because that one's a little bit easier. We see that net force in the y direction is equal to the forces that point up, force normal, minus the forces that point down, which equals mass times acceleration in the y. We know it's not moving in the y direction, and since it's not moving in the y direction, it's not experiencing any acceleration in the y direction. Therefore, acceleration in the y direction is just 0 meters per second squared. That's going to tell me that force normal minus force gravity is equal to 0, which is just telling me that force normal equals force gravity. Now let's take a look at net force in the x direction. Net force in the x is equal to the forces that point to the right, force tension, minus the forces that point to the left, force friction. That equals mass times acceleration in the x direction. In this case, we do have some x acceleration, and if we look in our problem above, it tells us that that x acceleration is 2 meters per second squared. So we're going to go ahead and fill out what we can with what we know, which would be force tension minus force friction is equal to mass times acceleration. Well, the mass in my problem, it tells me right here, is 30 kilograms. The acceleration is 2 meters per second squared. So I have 30 times 2. I'll come back to this problem in a second after I make my table. So here's our force table, just like we did above. We said before that force gravity is equal to mass times gravity. Therefore, force gravity would just be equal to 30 times 9.8. That's going to tell me that force gravity is equal to 294 newtons. I found out here, though, that force normal equals force gravity, so that also means that force normal is equal to 294 newtons. If I keep looking at my problem to fill out the rest of my table, I can see right here that the force of friction between the box and the ground is 30 newtons. So this is my force friction, so I can use this number in my table below. Now that I know what my force friction is, I can go and plug it into my net force equation in the x direction and solve for force tension. I find out that force tension minus force friction, which is 30, is equal to 30 times 2, mass times acceleration, which is 60. I'm going to go ahead and add the 30 over to the other side, and I get force tension equals 90 newtons. So let's go ahead and take a look at our third example here. And the third example just says a 1,200 kilogram elevator slows down as it reaches the top floor at a rate of negative 1.5 meters per second squared. What is the force of tension supporting the elevator? So let's go ahead and look at this problem really quick and see if we can identify any important pieces of information. I see right here 1,200 kilograms. Well, that's referring to my mass. So I'm going to go ahead and label that. The elevator slows down. Slows down is going to tell me that there are unbalanced forces. It also gives me a rate of negative 1.5 meters per second squared. This is telling me the acceleration, and I can clearly see that this acceleration is negative, which makes sense because my object is slowing down, so it should have a negative acceleration. Lastly, it just wants me to find out the force of tension supporting the elevator, so it's a little hint that in my free body diagram I should have force tension. Now let's go ahead and let's draw a picture of this elevator. So here's my elevator. The problem told me that there's force tension, so I'm going to go ahead and draw that cable right here, and I can just label it so that we know that there's a cable here so other people know that there's force tension. I'm going to go ahead and label my origin, point up as the positive y direction, and to the right as the positive x direction. In this case, there's not going to be any x forces because my elevator only moves up and down. My problem told me that I had a negative acceleration, which means that I'm going to have a negative net force. Which, if I'm looking at my origin over here, up is the positive direction, so my net force is going to end up pointing downward because that's considered the negative direction. Now let's go ahead and make this free body diagram. So here's my elevator. I always start with the same force, and that's force gravity, which points down. I told you right here that my net force is going to point down because it's a negative value, which is just telling me that my force gravity is going to be bigger than my force tension. So I'll go ahead and draw force tension pointing up. And again, like I said, force tension will be smaller here because I know that I am accelerating in the negative direction. So acceleration in the negative direction is going to result in a bigger force pointed in that negative direction. I also know that these two forces are not the same size because it tells me right here that I'm slowing down, which means unbalanced. Since we can see that there's only forces acting in the y direction, we only need to make a net force equation for the y direction. So net force in the y direction is going to be equal to those forces that point up, force tension, minus the forces that point down, force gravity. That is also equal to mass times acceleration in the y direction. Now that we have our equation, we're going to need to start plugging in some values into these variables. But we need to figure out what variables do we already know. Well, in the problem, it told us mass, so we know mass. It also told us acceleration, so we know acceleration. It did not tell us force tension, and technically it didn't tell us force gravity. But fortunately, we have an equation for force gravity, and that equation is force gravity equals mass times gravity. I know what mass is, and I know what gravity is on the Earth, so I can solve for force gravity. If I do that, I get force gravity is equal to our mass, which is 1,200, times gravity, which is 9.8. I multiply and solve, and I find out that force gravity should be equal to 11,760 newtons. So now I do know force gravity. So now I do know what force gravity is. So I'm going to put a check mark up there. Since I have 3 out of the 4 variables, I can go ahead and solve for my force tension. So force tension minus force gravity is 11,760, is equal to mass, which we said is 1,200, times acceleration, which is negative 1.5. I do some algebra here, figure out that force tension is equal to negative 1,800. Then I go ahead and I add my 11,760 to the other side. And now I just simplify and solve. This tells me that force tension should be equal to 9,960 newtons. Now that we have force tension, we're done with the problem. But if I wanted to add a little bit to it and say, what is the net force on this elevator? Well, we could figure that out two ways. We could say net force in the y direction of the elevator is equal to force tension minus force gravity. Or I could figure out net force of the elevator just by taking mass times acceleration. Both of these will give me the same answer. It doesn't matter which route I take. So if I do that, I'm going to figure out that net force in the y direction should be equal to negative 1,800 newtons. I ended up with a negative net force, and in regards to this problem, since it's acting in the y direction, that just means that I'm experiencing a bigger pull in that downward direction. Let's take a look at our last example here. And the last example is going to be a driver of a 1,000 kilogram car hits the brakes and the car comes to a stop in 3 seconds. The car was initially traveling at 25 meters per second, and we want to figure out what is the force friction required to slow down that car. Let's take a deeper look at this problem and see if there's any important information. I see 1,000 kilograms, that's talking about mass. I see that the driver hits the brakes and the car comes to a stop in 3 seconds. 3 seconds is talking about time. I also see that the car was initially traveling at 25 meters per second. That sounds like an initial velocity here. And it's asking what is the force friction required to slow down the car. Slowing down the car is telling me that there are unbalanced forces acting on this car. So this problem is actually going to be a little challenging, but a lot of fun. The reason being is that we're going to need to use some stuff that we already know. And that stuff that we already know is going to be kinematics. So why do we need kinematics? Well, we're going to need that to first solve for the acceleration. So let's do what we've done before, how we go ahead and we draw a picture. So here's my road, here's my car, and my car is moving on this road initially at a velocity of 25 meters per second. And then it comes to a stop somewhere over here, and we know that that is 3 seconds later. I'm going to go ahead and label my origin so I know exactly what's positive and what's negative. Up is the positive y, and to the right is the positive x. That also tells me what my initial distance and my final distances are. So let's go ahead and label our variables just like we did before for kinematics. Don't forget, we have dO, dF, VO, VF, A, and T. Initial distance, well, it's starting at the origin, that should be 0 meters. Final distance, I don't know how far it's ending. Initial velocity, 25 meters per second. Final velocity, well, they put on the brakes and they come to a stop, so that should be 0 meters per second. Acceleration is what we're solving for, and time is 3 seconds. It tells us how long it takes to come to a stop. So we have all the variables that we need in order to solve for acceleration. So looking at the equations, I notice that the one I want to use is little pup. So I'm going to go ahead and write that down below. VF equals VO plus A times T. Now I'm going to plug in my numbers into the equation. 0 equals 25 plus A times 3. Subtract the 25 over and divide by 3 to give me acceleration. I find out that the acceleration of my car is equal to negative 8.3 meters per second squared. It's a pretty big acceleration. Now that I know the acceleration of my car, I can go back to approaching this in terms of forces. So the next step for our forces is going to be to draw a free body diagram. So here's my car. I know my car is feeling a force of gravity pointed downward. I also know that my car is on a surface, so it should feel a normal force pointed up. I know that these two things are balanced because my car is not accelerating in the y direction. And then I also know that my car is slowing down, so it should be experiencing a force in the opposite direction of motion. In this case, that would be friction. Again, this symbol is the same thing as just saying FF. Either one will do, but I'll change them out so you guys can see both. So I'm going to start with writing my net force equation in the y direction. Net force in the y is equal to the forces that point up, force normal, minus the forces that point down, force gravity, equals mass times acceleration in the y. Since our car is not experiencing acceleration in the y direction, we find out that force normal minus force gravity is just equal to 0, which is just telling us that force normal equals force gravity. This makes sense because we said that we were balanced and our car is not accelerating in the y direction, so this is exactly what we would expect. Now let's take a look at the x direction. Net force in the x is equal to the forces that point to the right. Well, there's no forces pointing to the right, so that's 0, minus the forces that point to the left. Well, there's only one, and that's force friction. And we know this is also equal to mass times acceleration in the x direction. So if I simplify this a little bit, I just end up with negative force friction is equal to mass times acceleration in the x. Now that I have all my variables, I need to figure out what values each of these variables has. So I'm going to go ahead and draw my table like I did on my other problems. So let's look at the y direction first. I have force normal and force gravity. I need to remember though that force gravity is just solved for by taking the mass and multiplying it to the gravitational pull. So therefore I would get force gravity equals 1000 times 9.8. I find out that my force gravity should be 9,800 newtons. Since force gravity and force normal are equal to each other, force normal is also 9,800 newtons. Now let's take a look at the x direction. Well, I don't know what force friction is. Fortunately though, I do know what the mass is, and I do know what the acceleration in the x direction is. So negative force friction should be equal to the mass, which is 1000, times that acceleration, which is negative 8.3. I multiply through, I end up with negative force friction is equal to negative 8,300 newtons. Get rid of my negative sign, and it just tells me that force friction is equal to 8,300 newtons. So it's important that we notice force friction is positive here because I'm only talking about the magnitude of it. So this force table is just addressing the magnitude of forces, but my free body diagram over here has the direction associated with those. The direction is what's making it negative or keeping it positive. When I ask for your final answer, I will ask for magnitude and direction. And you have to remember that magnitude is always positive, and direction in terms of forces will either be up, down, left, or right. Last little piece of advice that I have for you is that whenever you have a problem like this, always identify your given variables. And then from there, make sure that you draw your picture like we said before. After the picture should come the free body diagram. And then lastly, you should write your net force equation with the variables. Last step would just be to plug in your numbers into your net force equation and solve. Also, remember that magnitude is referring to a number and direction is referring to up, down, left, or right.